Okay, I think we are ready to start. Welcome everybody here to this room and welcome everybody that is watching at this colloquium from the web. It's a great pleasure to be here today and to introduce to you the fourth colloquium of this year's series. Colloquium of today has the title IceCube, Opening a New Window to the Universe from the South Pole by Professor Francis Louis Halzen. I don't think I have much to say about Professor Halzen. He's a physicist coming from Belgium, where he completed his studies and education. He has been working also as a scientist at CERN for a few years, and then moved as professor to Madison, University of Madison in Wisconsin in the United States, and as PI of the Amanda telescope, and followed up by the IceCube telescope at the South Pole. He is the concept designer, pioneer, and hero for building a detector operating in the Antarctic glacier and detecting astrophysical neutrinos. His scientific production is very rich, as demonstrated by the many awards that he has been received. If I start enumerating them, I will definitely miss a good fraction of those, so I don't even attempt that. The most recent is the Pontecorvo Prize, which he received for the pioneering design of a neutrino telescope in the ice and for the discovery of astrophysical neutrinos. Among students of today, of my age and earlier, is very famous for the book, Quarks and Leptons, together with Martin. Halzen and Martin is the opportunity today to meet him in person, and so please enjoy. Thank you very much.
It's a pleasure to be here. I probably came 15 times to Venice, to the telescope meetings. I missed the first one. I had to send my only collaborator at the time. And I'm really happy that I finally made it to Padova. By now you have seen, this is 4.5 lectures I gave at Asiago in the last 2 days, condensed in one talk. So you better get ready. I'm going to start by a little bit of history as an introduction to make clear that, why would you, get in your head of building a kilometer cube neutrino detector? There was actually a very good motivation for this, and I'll start by reminding you. You all know that in astronomy, there is a long history of looking at the universe in different wavelengths of light, and for the particle physicists, different energies of the photons. And so you see the list partially. There's no room for the radio map on the left. And, but something you should realize is that at some point around, I will try to use TV units in this talk. TV is a tenth of the energy of the LHC beam and was the energy of the Fermilab collider. So if you reach 100 TV, there is no astronomy anymore. You see, there's just nothing. Nobody has ever seen the sky above 100 TV. And the reason is very simple and unavoidable. If you have an object in the universe very far away and it emits 100 TeV or 1,000 TeV photon, it never makes it here because the universe is filled with microwave photons, 411 per cubic centimeter, and this photon will on the way meet a CMB photon producing a plus or minus pair. Once you have a charged particle, you cannot do astronomy because it's deflected by the magnetic fields in the universe, which we don't know much about, by the magnetic field in our galaxy, and so the sky is totally scrambled. And we know this very well because, of course, cosmic ray, protons and nuclei arrive at the Earth, and they're very easy to measure, except they were discovered 108 years ago, and we still don't know where they come from, and because they're charged, they have the same problem. So the idea is obvious, and actually nobody knows who has it. Everybody had it, that neutrinos were the ideal way to do astronomy. And so they are especially interested in, well, I don't have to tell you, they are neutral. In this talk, they are massless. The fact that they have a mass is totally irrelevant in this talk. And they actually are unabsorbed. The standard model tells you that if you produce a neutrino at the edge of time or the beginning of time, it arrives at your telescope, untouched. It goes through everything, including your detector, of course, and that's the problem. And so how large, of course, doing neutrino astronomy is obvious. I mean, how can you resist looking at this part of the sky nobody has seen? And you may ask, why do I stop there? Well, I don't know. It may go on forever. But we have seen cosmic rays of this energy. So this is at least like 1/4 of the universe in wavelength that we haven't seen. Now, to be honest with you, I'll show you one slide as for full declaration. The real reason most of us are doing this is that we cannot resist solving the idea of solving the problem of where does nature produce particles of 100 million TeV. And we have no idea how they are accelerated, where they are produced. And so Michael Unger reminded me once that if you use LHC magnets to accelerate that particle, you have to fill the orbit of Mercury. And I can guarantee you that's not how it happens. That's only, I'll tell you the speculations that we have afterwards, and they may not be much better. But this is the cosmic ray spectrum, and it goes from, on the left, from cosmic rays that are accelerated in the sun, in solar flares, to the particles here at the bottom end that I've been talking about. And actually, it's only 2 years ago that the Auger experiment definitely established that these particles come from, are accelerated outside our galaxy, although we all suspected that forever, of course. And so when you, as a theorist, you contemplate this problem, you know, getting to 100 million TeV is difficult, but it's doable in principle. What you realize is that these accelerators also have high luminosity, not just high energy. And the combination of the two is incredibly difficult to model. And after 108 years, we basically have 3 ideas. And basically 2, because there are cosmic rays accelerated in our galaxy and outside our galaxy, so there are 2 different problems. And so the textbook idea is shown on this slide, and I won't go into the details of this, but the only way to get the luminosity is to have somewhere a huge amount of gravitational energy and transform a few % of it into particle acceleration. And so theorists have invented shocks and magnetic reconnections and things like that, where you can actually do this. So every textbook will tell you that this is a supernova that exploded a few hundred years ago, and the shocks at the edge of this supernova remnant, there are high magnetic fields there, and that's where particles are accelerated. And we know from Zwickis in the 1930s that this can accelerate the cosmic rays in our galaxy. Now, what you saw there while I was talking is exactly the same thing, except the star collapsed to a black hole. And this is the same as that, except that the black hole there has a spin, and so the particles move along the spin axis. This is, you know, the standard picture. There is one other idea There are a few others I will not go into, but you know, you need streams of relativistic particles to make magnetic fields and to, by shocks, accelerate them. And so this is an active galaxy. It's a galaxy like ours, except it has a black hole that's still eating up its own galaxy. And so you have flows of particles onto the black hole. And as you see in this picture, you have flows of particles along the rotation axis of the black hole. And so what this black hole does, it has, the galaxy has a magnetic field just like ours. And it winds up the magnetic fields along the spin axis and makes beams of particles. This is well known to astronomers. This sounds like fantasy, but has been seen. And I always found it amazing when I entered this field, I'm a particle physicist, that a black hole does this in less than one term. So if you think you understand this. Now, where do neutrinos come in? In fact, neutrinos are produced from the decay of pions, kaons. And so you can only make pions if you have a proton beam. So if you make a map of the sky in neutrinos, you only see cosmic ray accelerators, which is what we are looking for. And so you can imagine, here is a proton accelerated in this jet, and this galaxy is surrounded by light. So these protons can, with, I mean, typically 10 electron volt photons, this proton can interact and make a pion, photoproduce a pion, and then the pion decays in a muon and a neutrino, and the muon decays into an electron and two more neutrinos. And this is just like a beam dump at CERN or at Fermilab, no more at CERN. You have an accelerator, which in this case is the collapsed object, and you shoot the accelerator in a target, and you produce particles, but only the neutrinos come out, and you have a directional neutrino beam. It's the same here, and these black holes, collapsed objects, are surrounded by dust, light, mostly light actually, occasionally molecular clouds. And so by P gamma, you can make a pi plus, which then decays into neutrinos. But remember, this will play a big role in this talk. You cannot have a pi plus without a pi zero. And the pi zero makes two gamma rays. So every neutrino you may ever detect has a gamma ray of twice the energy, actually, when you look at it, because this pion decays in 4 particles, the gamma ray in 2 photons. And so for a couple of decades, theorists tried to estimate what type of detector you need to build such to solve this problem. And this was presented at, in 2012, and I like to show it because at that time, IceCube had been running for 2 years and we had seen nothing. And so this is what we presented as the motivation for this detector. Now, these beams are not monochromatic shock waves, and these things make beams that fall as 1 over the energy square. So it's a spectrum of energies. And so I multiply the flux here by E square so that the predictions fall on a line. And here you see supernova remnants, gamma ray burst, the movie you saw. And I will not go into this GZK neutrinos for those who know what that is. But you see all these predictions fall on a line. And so the suggestion was that if you build a fully efficient kilometer cube detector, you would detect these predictions somewhere in this decade. If you are there 100 events per year, there 10 events per year. So for a first discovery, this was a good bet, except nobody knows what the errors on these calculations are. And in fact, we haven't seen any of these things, but we have seen cosmic neutrinos. What is this? Well, this is the atmospheric neutrino flux. IceCube detects a neutrino every 5 minutes. But it's a neutrino that's made by cosmic rays interacting with nitrogen and oxygen in the atmosphere, making pions and muons, and the pions and muons decay and make neutrinos that go through the detector. And if you go deep underground, there are fewer of them, but if you build a big detector, they come at a high rate, as you will see later. So that was very much the motivation. And you have to remember one number from this slide, 100 TeV. You see, we measured the flux of atmospheric neutrinos with Amanda and IceCube for many years. You can calculate this flux, we understand it, we know how to extrapolate it. But the important thing is, if you are above 100 TeV, a few hundred TeV, there is no background, so every event is a discovery. If you go below 100 TeV, this is a log scale, it's hopeless. So that's the critical thing to remember. Energy measurement is the key of your energy measurement of your detector. But you see, we have measured the atmospheric neutrino flux over many orders of magnitude. So this experiment is calibrated. It's important to remember. So IceCube, how do you build a kilometer cube detector? That was known since 1960. Markov, this is what he said, but the idea is simple. Your telescope looks through the Earth, so you look for neutrinos coming through the Earth, and they will just move through your detector. But 1 in a million at these energies will interact with a nucleus and make a muon by well-known standard model physics. And the muon range, in this energy range, muons travel kilometer to tens of kilometers at 1,000 TeV energy. And so you can detect these neutrinos to far outside your effective instrumented volume. And so what you do is, if this muon happens to reach your detector, you fill a kilometer cube of some transparent water deep in the ocean or in Lake Baikal, which was Markov's idea. And then you measure the Cherenkov cone of this muon, because it moves at the speed of light, and the speed of light in water is 3/4 of the speed of light. And the Cherenkov cone measured by your photomultipliers will tell you the direction. And at these energies, everything is aligned. So you not only detect neutrinos, you have a telescope, you know where they come from. So you would think, well, photomultipliers and water, I've seen this before. And, sorry. Here is the Super K experiment. And this is perfect, much better detector than IceCube. The minor problem is it's 10,000 times too small. And so that's why you need Markov's idea. This idea was tried out, and so eventually, in the late 80s, we had the idea in Wisconsin to instead of doing it in water, to do it in ice. And so the idea was to go to the geographic South Pole. So this is actually the geographic South Pole when this picture was taken. NSF has a research station there, the National Science Foundation, with the kind of facilities that allows you to build an experiment like this. And this is the IceCube construction site. And everything goes in and out by plane. And that's the landing strip, as you can see. Now, this was a good idea, history has shown. But we were also very lucky. Nobody had any idea what the Cherenkov properties of this ice were. And so this took a while to figure out, but below 1.35 kilometers, this ice is incredibly transparent, as I will tell you later. In fact, in the top of the detector, the absorption length of light is 200 meters. At the bottom of the detector, it approaches 300 meters. You cannot build a solid in the lab that has this transparency. And so it's 60,000-year-old snow. But we didn't know all these things when we started. And so here is the next slide. So you go, here is the surface. Here you have cables, and there is nothing on the cable for 1.5 kilometers. And then you have the cable is instrumented with photomultipliers to 2.5 kilometers. And then there is another 450 meters, and there is bedrock. And so here you see there are 86 of these cables, each of them containing 60 photomultipliers. So the kilometer cube is filled with 5,160 photomultipliers. So if you could go inside the detector, you would see this kilometer-long string every 17 meters, a PMT. And if you look 125 meters away, another string. And if you repeat this 86 times, you have IceCube. The easiest part of the experiment is you buy this in Japan. So it's the size of a basketball, and you put it in the ice. Before you do that, you put it in a glass pressure vessel. And you see there is some electronics, not in Amanda. What happens is that all the photomultiplier signals are captured by 2 chips and a flash ADC, and then digitized. And so the cable that brings down the voltage takes back up the digitized signals. And each of the photomultipliers runs as an independent experiment. Here you have an example. So as a function of time, the photomultiplier will send you a signal of the number of photons detected. I'll refer to this as a waveform. We have 2 nanosecond timing across the array. And so a timestamp is put on this picture and then sent to the computers at the surface. And so here you see a picture. That season, which is 2 summer months at the South Pole, 20 holes were instrumented. And you see the cable goes to this 2-story building, and the 2-story building has nothing but computers and it collects all these signals and put them together in events. So what do you see, actually? Well, at the South Pole, you will see from the southern hemisphere cosmic ray muons at a very high rate. And you will collect neutrinos from the atmosphere everywhere on Earth. And you hope to find astrophysical neutrinos. Remember, 10 to 100. And here, this is a movie of the detector taking data. And you see, whenever a dot gets colored, it's a photomultiplier that collected a signal. And so the computers make fit muon tracks to this data coming in. Here you see at some point a big muon bundle going through to the detector. This movie is 10 milliseconds long. And so what this amounts to is, I have another movie. Here, this is the Disney version. Here you see the Cherenkov flight made by a cosmic ray muon coming down. And so this is the response of the detector. So a small dot is 1 photoelectron, and a bigger dot on this picture is like 50 photoelectrons. So, but in actuality, each of these dots is a trace of light detected. And so the size is the number of photons, and the color tells you the direction. So the bottom line is that we detect 100 billion muons per year, 3,000 per second, 100,000 atmospheric neutrinos. Now it's more like 1 every 5 minutes. And in fact, I can tell you the answer. We discovered 120 cosmic neutrinos per year. But before I get there, to avoid all the questions of how you put photomultipliers in ice, here is a short movie. The top 80, 90 meters is snow, so you just melt it. Remember, you have to put like basketball size photomultiplier. This is the hot water drill, and it's just a nozzle that puts out hot water under pressure, and it melts the ice just falling over gravity, through gravity. So after 2 days, it's at 2.5 kilometers. Then you pull it out. So it takes, to produce the hot water, you need 5 megawatt heating plant, which is like 40 car wash heaters. And so here you see the picture, you saw the data, 90-degree water under pressure. And this is the hose. It's about this big. And it goes in one shot to 2.5 kilometers. I'll come back to this in a minute. And here you see the modules with, it's like a circus train, right? It are like containers. And the generators and the car wash heaters, they're all built on sleds. And then the sleds go from hole to hole. So this is a critical moment when the drill comes out of the hole, you will see, and then you move on to another place. And you see here is the drill tower, to just move on. But waiting at this site are the 60 digital optical modules. You see they are lined up. And so there's no string. You lower, as you will see in the next frame, you lower a cable, and the cable, every 17 meters, you attach a module, and then when you have instrumented a kilometer, you let the whole thing sink to the bottom. You wait until it refreezes and take data. You have to remember, ice is an insulator, so that water remains liquid for quite some time. It's not like you have to hurry. So we built this detector in 5 years, and so now, to make a long story short and come to the point, this is a muon going through the detector, and it comes from 11 degrees below the horizon. You see, you follow the rainbow, red to green. It's coming through the Earth, so it's a neutrino. And so you are seeing exactly this, right? The muon coming from below the horizon. And in fact, this muon deposits 2,600 TeV inside the detector. That means if you do a standard model calculation, the neutrino energy is something like 7,000 TeV. And remember, the critical number was 100 TeV, right? That's where your background disappears. So this event is close to a 5 sigma discovery by itself. But of course, after 3 years of data, which means at that time 550 cosmic it says 550 atmospheric neutrinos. You see here, I don't even bother to show the data, but this is the atmospheric flux. And you see when you come to 100 TeV, you see the cosmic components sticking out. This is the event I showed, which of course, at that time, we have now an event which has energy above 10,000 TeV. So this is not a record event anymore. And it has a slope of e to the minus 2.19, which is kind of what you expect. And it has correspond to 120 muon neutrinos per year. Oh no, it says correct. It is 500 cosmic in 340,000 atmospheric, 3 years of, yeah. And so, of course, this is exactly what we expected. And except, as I said already, these are not the things that we see. Here is a record event which came not so long ago, and it deposits 5,300 TeV inside the detector. It actually confused the reconstruction, which was kind of a disaster, which you will understand later why. So this is actually not how we discovered cosmic neutrinos. This was the way we were supposed to discover them. But we were looking for these GZK events, they're events of 1 million TeV. They are made by cosmic rays interacting with the microwave background. And we didn't see any in the first 2 years of data, but accidentally we found 2 events like this. And this event is beautiful because you see the whole Cherenkov pattern is contained inside the detector. So you know exactly what the energy is. And the energy is the critical thing you have to measure to establish it's cosmic. So we found 2 events that are at an energy of about 1,000 TeV. They have no muon track. And when they interact, they don't make a muon. Say an electron neutrino gives 80% of its energy to an electron, and then an electron will shower in the ice. And the shower is about from here to the wall, but that, in a kilometer cube detector, is a point source of light. And that's what you saw. You saw this ball of light made by this shower. It's about 7 meters long at this energy. So that was great. Suddenly we were given 2 events. It was almost 3 sigma discovery. We didn't claim anything, but looked through our data. We first modeled these events, and you see this is a picture of a simulation of that event. You see it's totally spherical, but look at the colors. It was red and yellow, now it's yellow and blue, and that is because the neutrino came in this way, and so the phototubes there are reached by the Cherenkov light before the ones in the back. And from that you can reconstruct the direction of this event. Not very well, but we're working on that. You have to rescale what you are looking at, right? This is the campus in Madison, and this is the event superimposed on the data center. So it's like if you go into city, like 5, 6 city blocks, probably more in Padova. And so this event has more than 300 sensors and more than 100,000 photoelectrons. We know where each one is to 2 nanoseconds. And so that's a lot of information. And we are now can reconstruct these events to better than 5 degrees. But to do astronomy, this is basically useless. However, with this method, and I won't dwell on this in detail, you actually now can see all 3 flavors of neutrinos, and you can see the whole sky, not just half of the sky through the Earth. And so we designed an analysis which was very complicated with a veto, which was only, was in software, but basically the idea was to catch events where no light comes in and you have a neutrino starting in the detector. And then a student finally noticed that if we just plotted our data, you could see the signal. This is 1 year of data of starting events, so-called starting events. This is the total charge in the event, and this is the charge in the veto region, which you can think of as 6 photomultipliers at the top to shield cosmic ray muons, and 1 everywhere else. And you see, so what you are looking for is high energy events, and you have 0 light coming in the detector, and so you can see the signal sticking out. And so every year of data we have is like this. And that's what we finally published. We found 26 more events, plus the 2 we had found by accident. So we have now 2 methods and they are completely different. Use different method, different software. It's like having Atlas and CMS, but with only one piece of instrumentation. And of course, what confirms these events are cosmic, if they come from far away, every flavor appears equally in your detector. They have oscillated to equal nu e, nu mu, nu tau. And you see this diagram here. And I could go on, so this is what you expect. This is what we measure. And so, of course, we are now measuring neutrino oscillations at 1000 TeV energy. That's, of course, very interesting. And I could spend the rest of my talk going. We are building, actually, an upgraded detector in a few years, 2022, to make this measurement with smaller error bars. So we detected cosmic neutrinos two more ways. It's very difficult to tell a nu e from a nu tau, but we managed to get some information. You know, nu taus were discovered at Fermilab in an emulsion experiment, because in an emulsion experiment, you could see the tau being produced and decay. They have a track length of a few millimeters. Well, when you go from the energy of Fermilab to our energy, this track length at 1000 TeV, it becomes 50 meters. So you look for events where the tau interacts, the nu tau interacts, and it makes a normal ball of light, like you saw. But then the tau travels and then decays, and it makes another shower. So in this event, you cannot see the two showers, but you can see, when you look at signals in the photomultiplier, you can nicely see the photons produced when the nu tau interacts. This is the deep inelastic scattering, and this is the tau decay. And so this event, the lifetime of the tau, 17 meters, which means it's like a 300 TeV neutrino. And this event was found in 3 different analyses. And so we have found some more candidates, and so we are in the business of measuring oscillations. We recently found another, this really shouldn't be part of this talk, but I cannot resist showing it. You know, neutrinos only interact with nuclei. That's why they have this small cross-section. But there is one way neutrinos interact with atomic electrons. That is when an antineutrino interacts with an electron, makes an ATGF, a real W, which then decays in 2 jets. If you transform the ATGF mass of the W into the lab, that's 6.3 PeV, 6,300 TeV. And this event was found in an analysis which I won't describe. It's just outside the detector, and you measure the energy, and the deposited energy was 5,900 TeV, and our Cherenkov detection efficiency is 93%, so it's right on the money. And so here you see, this is deep inelastic scattering, this is this resonance. Of course, this washed out by a resolution, but you see here is the energy reconstruction of this event. And you see our energy resolution. We were all excited about this, and you won't guess why. We had our calibration correct. This was the first clear evidence that we had nailed the calibration of the detector. Anyway, so by now we have discovered, because a nu tau, by the way, of this energy cannot be produced by oscillations in the atmosphere. It's another independent discovery of cosmic neutrinos. And so this is the status of these measurements. This is the flux of nu e and nu tau. This is the atmospheric flux. I didn't explain to you how we eliminate the atmospheric background here, but notice it's not very large. And this is the flux in muons, and they are all perfectly consistent. But of course, you know, we have to do better, make better measurements of this. So the critical question is, where do they come from? And so I can show you a map of 1 year of data, and I cannot show you 10 years, which we have now because PowerPoint cannot handle the resolution. And you see this map is totally uniform. What you see here, I leave as a homework, but it has nothing to do with cosmic neutrinos. And of course, you don't see anything because these are overwhelmingly atmospheric neutrinos. It should be uniform. So let's just look at the events above 100 TeV or so. And then you look, and it's still consistent with totally uniform. And the big surprise is this is in galactic coordinates. First, you are supposed to see the nearby sources in your own galaxy, and then sources outside the galaxy. And you see there's absolutely nothing. In our galaxy, the events should cluster around this, the major axis of this ellipse. And a warning to people who like to do science with small statistics, I will do it in 15 minutes. This was the first event we measured. It came right off the center of the galaxy. And at that time, it took a whole day to reconstruct an event. I went home totally depressed. You know, I didn't want to see the center of the galaxy. And anyway, there's no evidence for the center of the galaxy. So we are about to publish our 10 year of data. And for the first time in the 10-year analysis, we see non-uniformity in the map. There is a 3 sigma, not 5 sigma, but 3 sigma asymmetry in this map, which you cannot see by eye. And it's due to these 4. So, of course, if you don't see a clear signal, you put a limit on the flux as a function of, this is basically the zenith angle. These are downgoing, the horizon upgoing, so you're scanning the sky. And you see these 4, there are 4 sources that almost 5 sigma pre-trial. But one of them, NGC 1068, actually is 3 sigma post-trial. And the second one is TXS 0506, and you will see that name later. But here is the other spot. Now, the interesting thing is, we also, besides this, make a list a priori of 100 sources that we think could be really cosmic accelerators and that we could possibly see. And the hottest source in that list is this one, and it happens to be the same position as that one. So very, not a discovery, but it becomes very interesting. In fact, this galaxy is an active galaxy that every theorist knows and loves. It's M77, and this is not a theory seminar, so I will resist. So we observe a diffuse flux of extragalactic sources. The sky map reveals structure at the 3 sigma level associated with 4 sources. A subdominant galactic component is emerging, but it doesn't reach the 3 sigma level. We see the same sources as high-energy gamma-ray detectors see in the 100 TeV region, but they're only at the 2 to 3 sigma level. So now the question is, remember, for every 1000 TeV neutrino, there is 1000 TeV gamma ray. Nobody has ever seen 1000 TeV gamma ray. And okay, this was the slide. I explained this 1950s physics, non-negotiable. And I already told you, even if there were 1000 TeV gamma rays, they wouldn't make it here. But remember, this positron will not stop. It will radiate. and then this photon will pair produce. You have to conserve the energy. And so this 1000 TeV photon that goes with a 1000 TeV neutrino, it will just produce a shower on the microwave background and comes out as many photons of lower energy, 10 GeV. And we have a satellite that perfectly measured photons in this energy range. And so we can see what that gives. And so here is the neutrino data. This is a historic plot. So that was the data at that time. And I remember one of my collaborators drawing this line. And it doesn't matter whether you cut off or not. You have this flux, which kind of, I quoted 2.19 before. Now you take this and you say there is an equivalent gamma ray flux. You take a computer, process it through the microwave background, see what comes out of Earth, and what comes out on Earth is this. And you see this is the extragalactic flux seen by this Fermi satellite. So that's interesting. Can you avoid this? Because it's quite shocking conclusion, as you will see. Well, I can fit the data this way, and then I get less photons in the Fermi detector, but you must agree this doesn't really fit the data. This is a really intelligent model, and so it's good to test. But still, so it's unavoidable that within a factor, you're in a factor of this flux. Now you may see, well, you don't fit that point. And in fact, we have a lot of evidence that there are events out there from other analyses. So I fit that point, in fact, not quite, and this is the answer now. So the conclusion is that it's impossible not to have this extrapolation fall, this extrapolation of the energy in gamma rays fall very close to the Fermi data. And so the conclusion you draw from this plot is that the energy in the universe in neutrinos and in gamma rays is roughly the same within a factor. And that, of course, comes as a surprise to astronomers that describe all of astrophysics, high-energy astrophysics, with electrons and photons, and ignore cosmic rays as some exotic phenomena. Well, that's not possible anymore. I mean, you cannot understand the universe now without understanding neutrinos. So the next question you may ask, are we actually seeing the same sources? Because by now, you know, we have tried for about 3 years at this point to correlate our maps of the sky with anything you can think of. I challenge you. And never found any correlation. So we have no clue where at this point where these sources come from. So Fermi knows most of these photons come from blazars. And blazars is the thing I explained, where you have a jet going perpendicular to a spinning supermassive black hole. And so what I just showed to you is this picture, but with not just the neutrinos, also with the pi zeros that make a photon shower and which perfectly fits the Fermi data. So despite all that, there was for 3 years, it was very frustrating. And so then in desperation, of course, building a neutrino detector is already desperation. The next desperation was to, so whenever we detected a high energy neutrino that had a good chance to be cosmic, the South Pole, at the South Pole, these tracks are reconstructed. Then they are sent over satellite to Madison, where they are further reconstructed, and then they are sent to the collaboration. So we decided whenever we detect an interesting neutrino, we send the coordinates immediately to the astronomical community. by some system called astronomical telegrams. I had never heard of it when we started doing it, but it's a pretty frightening thing because I won't discuss this slide, but what it means is that within less than a minute of the neutrino being detected, the results of your experiment are made public in the whole world. And all you get is a picture on your telephone. But it's gone. It's too late at that time. So the 10th alert we sent was this one. It was sent within 43 seconds of being detected. And you see it gives the coordinates in the sky. And then it tells you that the energy here, you see, is 1200 TeV. So it's interesting. In fact, the energy upon detailed reconstruction is 290 TeV. And so it's cosmic neutrino, most likely. It's an event like you've seen before, perfect detector working. By the way, the detector works as an on-time of 99.5 in a bad week and 9 in a good week, and has been going uninterrupted. So we actually had no idea whether anyone paid attention to these telegrams. But then we found out, after a couple of days, someone told us that within 0.06 degrees of this muon, there was one of these Fermi blazars. And that's interesting, but there are a lot of Fermi blazars. But this blazar had increased its flux in the last few weeks by a factor 7. So that's also not too unusual, but having a flaring blazar on top of this neutrino, that was interesting. And so all of us started calculating what the probability of this was. And the answer, everybody agrees to, is like 1 in 1,000. Probably better, but 1 in 1,000. 1 in 1,000 happens. So it's what makes this event real is what happened afterwards. Because there was a telescope in the Canary Islands, our friend from Magic and Felisa, who detected from the same source 100 GeV gamma rays. So it's not only a flaring blazar, it's a TeV flaring blazar, which is really more unusual. And in fact, we now know that these are actually TeV gamma rays that cascaded in the microwave background. So here is, I have to show a picture of magic. It is magic. And so we also got the answer whether when anyone looked at our events, because at some point 22 telescopes had looked at this event. And in fact, the first to detect it was Swift in X-rays. Here is Fermi, and here is MAGIC. The other satellites were trying to identify the source. But the high energy radiation was so strong that you couldn't see lines. And so it was impossible to see the galaxy. And so after a while, when the high energy radiation had tapered off, it was found that this blazar is at 0.34, that's 1.7 gigaparsecs, or 4 billion light years. Now, this again was a shock, because there are sources exactly like this, which are 10 times closer, and we had looked for desperately, never seen. So this was actually the brightest thing in the sky at that time. So here is a summary of this multi-wavelength campaign. And so this is actually where it becomes interesting. We actually have archival data. So we had 10 years of data, and someone now had told us where to look. So we look back at our data, and here it is, 9.5 years from that direction in the sky. And so you're looking at the wrong thing now. This is what I have been talking about. This is what we had seen in 2014. It was a flux of 13 events in 110 days. And so the chance, if you look with a prescription at data, there was no analysis, is mathematically a few times 10 to the minus 5. So this is real, combined with all the other things. In fact, there are enough events to measure the spectrum, and it's 10 to the minus e to the minus 2.1. So the first question is, why didn't you see this before? Well, we did see it before. There it is. And so this is amazing because its whole flux in 9.5 years comes from 110 days in 2014 and 15. And despite it only was on for 3 months, it competes in the total flux contribution to the sky map. This map doesn't take into account flares or anything. So we have identified a source. Okay, I think I said all that. And of course, because of this source, this is the flux times e squared. And you see it was measured in all wavelengths. It's a beautiful set of data. Except that you now know there is one neutrino. In fact, there are a few more of low energy, not very exciting. So you may remember this picture if you are old enough of Cabibbo, and I like to show it. So what happened is that theorists dug up their models for blazar. Blazar was supposed to be well understood. And guess what? They couldn't produce one neutrino. And they tried very hard, 14 parameters for not getting one neutrino. And of course, when I was talking, I knew already that there were 13 in 2014-15. So, you know, it's not you see one neutrino, it blows up the whole understanding you think you had, right? And so this is slowly being resolved. I'm going to just show a few slides, but what's happened is interesting. You know, if, first of all, so we are looking at some special class of sources. Our next game is to identify these, and that may be the answer to the cosmic ray problem. I cannot read the future. But actually, if every blazar Fermi saw was like this one, we would overproduce our diffuse flux from the sky by a factor 20. So blazars is not the answer. What Fermi calls blazars is something else. And it has a jet, presumably. Also, if a beam dump produces 30 neutrinos in 3 months, it has enough target density to produce the neutrinos. That target density, high energy photons cannot get out. And indeed, during the burst, there was something going on in the Fermi data, people argue, but there was no flare, and it's impossible. You need an opaque target to make 30 neutrinos in 3 months. And so the conclusion we made, we even published, is that we are looking for some new class of sources. And you know, the argument I made is extremely simple. You can calculate on the back of an envelope. There is no photon beam accompanying the CERN beam or the Fermilab beam. And so this is where the situation stood. And of course, in 2014-15, there was no multi-messenger campaign. We hadn't sent an alert. This was before. So the only data people start to look, they found radio data. And so it turns out that the source was actually flaring in radio. And they saw the core around the black hole expand. And so this had been going on for a few years, actually. So there was, it had been brightening in the radio, and the neutrino came in the rise of this brightening. So there were a couple of papers published on this. Here is one, another one I won't go into. In fact, there were people who claimed that they could see 2 jets in the radio picture. These are all VLBI data, where you couple telescopes to look at the source and make high-resolution images. And so you see, these people claimed they could see 2 jets, and that it was in the interaction of the 2 jets that you found this big target. I wouldn't bet my money on this. But so now the radio came in the picture, and they also had kept their data, right? So here is the radio data. This is where the 17 neutrino is. And you see it started rising around the 14, 15 burst. Now, in July of last year, we actually sent another alert. It pointed back at this active galaxy. And people again looked in radio, and it turns out again that this source was flaring in radio. So, you know, this is reading tea leaves, but we keep, you know, finding ways to corner the problem, not just by building bigger detectors, but by, you know, getting more and more tools to work on this problem. And in fact, we managed to get the astronomers, at least some of them, pay attention to cosmic ray physics. And have we solved the cosmic ray problem? No, but I think we have a very good tool to get there. And when you listen to this talk, I mean, I don't have to show you any slides to realize what we could do if we had 10 times more data. And so you can actually build 10 times bigger detectors. And so we are just started on our way to do this. And of course, you all know in Italy, SKM3Net has a plan to build 6 times the volume of the sensitivity of IceCube. So I think we are on our way. You know, every cosmic ray detector has been built allegedly to solve the cosmic ray problem, but I think actually we have the tools here to solve the problem once and for all. So stay tuned. I don't have many conclusions. The important one is cosmic ray neutrino astronomy exists. We need more neutrinos and more telescopes. And I want to show you a picture of my collaborators. Thank you.
Much, Francis, for this wonderful presentation.
Thank you.
Are there questions, comments?
Yes, so you mentioned the gamma neutrino multi-messenger approach. Now, the next ambitious step would be to have also another messenger in the game with gravitational waves. So I was wondering if you have hopes to have some coincidence with the gravitational waves.
Yeah, well, of course, black hole mergers is out, right? There's no nothing. But for neutron star mergers, estimates have been made. And so the only neutron star merger we have, if we could have seen, it's at 40 megaparsec. This may never happen again. But so we are at a stage where theorists, you know, makes this band of predictions, right? Where you really have no clue what the error is. But now we have learned our lessons, so we make optimistic and pessimistic predictions. And so we would have seen the neutron star merger with IceCube with the optimistic prediction, and with the next generation, we would even have seen it with the pessimistic prediction. So it's in the range of sensitivity. That is provided the jet points in your direction. So we won't know the answer, but the jet is rather broad, we think we know now. So we'll need many neutron star mergers before we know the answer, but and that may take some time too.
Thank you. If I am allowed, just a short second question is you mentioned that behind the kilometer cube here in Italy and in France, say. I was wondering, okay, apart from having a larger size and sensitivity, but the fact of having a neutrino telescope in the northern hemisphere, what are the strong points of this?
First of all, KM3net would be fantastic, right? Because you want a second detector to check. By the way, Antares has a 1.8 sigma enhancement for cosmic neutrinos, and Baikal is deploying, not completing, but after the deployments this spring, they should be able to make a first check of our flux. So these experiments are moving. It's, I mean, the other sky is interesting, but I think what's more interesting is that KM3net has its, it doesn't have this large absorption length, so it spaces its strings by less than 100 meters. And you know, we are going to space our string by 250. And there's no free lunch. The price you pay is that your threshold goes up when you space your strings. So KM3net will have a lower threshold than the next IceCube, and I think that's very important, especially for galactic sources, but God knows for anything else. This NGC source that we see at 3 sigma has a very steep spectrum. And so then again, the threshold would be critical. So in that sense, the complementarity is also important.
Other questions?
So you pointed to 4 directions in the sky, let's say, where you have some direction privileged for neutrino of medium-sized energy, okay? What I see before. And you say, well, that must be special region because otherwise we will have, if it is only blazar, we will have a more diffuse background. So basically you are inviting the astronomer to look to this 4 direction and see if you can see something.
Back actually was on my slide, and I didn't want to speculate too much in a colloquium, but if there are 2 jets, you realize people think this is a merger of 2 galaxies. And once you have a merger of galaxies, then, you know, there is a lot of material in which you can make neutrinos. So it's a whole new game.
Let me add something, but in some respect, it's not that interesting to look, let's say, in coincidence, because maybe the events are not coincident. The neutrino are coming at some point. So it's just a long-term study of these kind of sources to see the properties.
Well, the relation, as you saw from the, you know, in 17, we saw a flaring blazar, and in 14, we saw a lot of neutrinos, but nothing in gamma rays. There's something, there's some high energy photons, and we have modeled this, and we can explain the Fermi flux at the time, but Fermi would never have noticed it and told us, hey, look for neutrinos. So there is a connection, but it's a more subtle connection, and it depends in the end of what the sources are. If the answer is merging galaxies, and that's consistent with everything, it's a preliminary answer, then we have to start modeling this. And, you know, so of course already happening.
Sorry,
yes.
Okay.
Okay, congratulations, Francis, for this fantastic achievement. Shedding light on the origin of very high energy cosmic rays. Can you briefly sketch about plans for future developments of IceCube?
Our plans are very simple, actually. We want to basically deploy the same number of photomultipliers. Of course, the technology will be upgraded. And on a similar number of strings, but spaced over larger distances. So if you take this detector and space the strings by a factor 2, you get 8 times the volume. And so the cost of the next generation detector is the same as the cost of the last one. It's roughly there are more photomultipliers. The modules have become cheaper. The electronics has become much cheaper. So we're thinking about smaller modules, and so that the deployments can go faster and cheaper. So there's a lot of new technology going into this, but it's basically the same technique spaced by a factor of 2. And so the KM3 net techniques, they do, instead of big photomultipliers, they use many small ones, which solve some problems connected to the water, but the concept is the same.
Other questions? Comments?
So, in a way, this IceCube is a sort of new kind of telescope. So, could you comment on the angular resolution that we can achieve, and how does it depend on the energy of the events?
Yeah, I actually only pointed out where we have bad angular resolution. I didn't point. You know, obviously, the answer to your question is, you notice all the astronomy is being done with the muon tracks, right? And we reconstruct muon tracks depending on where exactly they are in the detector and what exactly their energy is, somewhere between 0.2 and 0.4 degrees. And so our goal is, that's again a whole other talk, our goal is to get, even with this detector, possibly to 0.1 degrees. And then we are as good as in resolution and size to gamma ray detectors. We should be able to do astronomy without doing multi-messenger astronomy. But yeah, that's one of our goals.
Any other question or comment? Okay. I don't see any, so
thank you.
let's thank the speaker again. Thanks.